In quantum mechanics, a free particle is defined by a single strict condition. It exists in a space where the potential energy, V of x, y, and z, is exactly zero everywhere. To determine the state of this particle, we rely on the Schrödinger equation. This serves as the quantum mechanical equivalent to Newton's second law, determining how the wave function behaves over time and space. Because potential energy is zero, the Hamiltonian is entirely composed of the kinetic energy operator. Solving this in standard Cartesian coordinates is straightforward. We get a plane wave moving smoothly along a single axis, characterized by its momentum vector k. But physical reality rarely deals with infinite empty space. Particles collide with targets, scatter off central forces, and interact with spherical atomic potentials. A flat plane wave lacks the symmetry required to analyze these interactions effectively. While Cartesian coordinates provide mathematical simplicity, they are physically insufficient for studying phenomena like spherical scattering. We need a coordinate system that matches the rotational symmetry of the physical world. Consider a scattering event. When an incoming plane wave strikes a localized target, it radiates outward as complex spherical ripples. In central force systems like this, the potential depends only on the distance from the origin. This means torque is zero, and total angular momentum is strictly conserved. It becomes a good quantum number. To describe the system accurately, we must find a set of simultaneous eigenfunctions. These are states that have definite values for the energy Hamiltonian, the total angular momentum squared, and the z component of that angular momentum. We accomplish this by abandoning the x-y-z grid. Instead, we transition to spherical coordinates, tracking the particle's position using the radius r, the polar angle theta, and the azimuthal angle phi. The quantization of angular momentum in these systems builds directly upon the foundational models proposed by Niels Bohr. Spherical coordinates provide the natural framework for these systems, natively compatible with the rotational symmetry and conserved angular momentum of the physical world. This equation is the Laplacian operator in its full spherical form. It contains the second derivatives with respect to the radius, theta, and phi. To solve this massive differential equation, we apply separation of variables. We assume the wave function can be split into a purely radial function, r of r, multiplied by an angular function. The angular portion is completely described by the spherical harmonics. Because these are already the established eigenfunctions of the angular momentum operator, we can substitute the entire angular chunk of the Laplacian with a single angular momentum term. This isolates the radial behavior into a one-dimensional equation. To simplify it further, we introduce a substitution. We define a new function, u of r, equal to r times the radial function. Applying this substitution reveals an additional term proportional to the square of the angular momentum quantum number, L, divided by the radius squared. This is the centrifugal term. This plot graphs the effective potential. Because the actual physical potential is zero, the effective potential consists entirely of this geometric centrifugal barrier, which forms a steep 1 over r squared repulsion curve that grows stronger for higher values of L. This geometric force dictates that particles with high angular momentum face an immense physical resistance, keeping them away from the origin. To see how this behaves, we start with the simplest physical case, an angular momentum quantum number of L equals 0. With L at 0, the centrifugal term vanishes. We define a wave number k based on the particle's energy and mass, which reduces the radial equation down to a simple second-order differential equation. The general mathematical solution to this reduced equation is a standard linear combination of sine and cosine functions. However, we must remember our earlier substitution.
The actual radial function, r of r, is this general solution u of r divided by the radius, r. This graph maps the behavior of that cosine term divided by r. Notice that as the radius approaches 0, the value of the function diverges, shooting upward to infinity. Quantum mechanics requires that wave functions represent physical probabilities. A probability cannot be infinite. Therefore, the wave function must remain finite at the origin to be normalizable and physically valid. Because the mathematical solution must conform to physical reality, the coefficient b for the cosine term must be strictly 0. For a particle with zero angular momentum, the sinc function, the sine of kr over kr, is the only valid radial solution. We now return to the full radial equation to handle cases where the particle has angular momentum, meaning L is greater than 0. To find a solution, we first transition to a dimensional variable, x equals kr. This scales the physical distance by the wave number, allowing us to factor out the energy and mass constants from the Laplacian. When we rearrange the radial derivatives, the equation takes the specific form of the spherical Bessel differential equation. The solutions to this established mathematical equation are defined by two independent sets of functions, the spherical Bessel functions, JL, and the spherical Neumann functions, NL. When we examine the algebraic form of the Neumann functions, we find the variable x consistently present in the denominators, even at higher orders. This comparative plot contrasts the two solutions near the origin. While the spherical Bessel functions approach 0 or a constant value, the Neumann functions dive towards negative infinity. We apply our physical boundary condition one final time. Because the Neumann functions blow up at the origin, they cannot represent a physically localized free particle, and we discard them entirely. Defining the precise energy scales and constants that govern these wave functions relies heavily on the original physical frameworks established by Max Planck. The rigorous elimination of divergent mathematics leaves us with a single conclusion: the only physically acceptable radial solutions for any free particle in three-dimensional space are the spherical Bessel functions. We can now assemble the final stationary state. The full 3D wave function for the free particle is the product of a normalization constant, the spherical Bessel function for the radial part, and the spherical harmonic for the angular part. There is a subtle physical problem remaining. Because the wave number k can take any continuous value, integrating this stationary state over all space yields infinity. It is technically non-normalizable. To represent a real particle, we construct a wave packet. By superimposing an infinite number of these stationary states with slightly different values of k, the waves interfere constructively in a specific region and destructively everywhere else. These infinite stationary states serve as the mathematical basis vectors needed to construct the localized wave packets observed in actual experiments. This leaves one final question. If a plane wave and a spherical Bessel state both describe a free particle, how exactly are they related? The bridge between Cartesian and spherical descriptions is provided by Rayleigh's formula. It equates the plane wave to an infinite sum of these spherical states. Through this formula, a flat plane wave decomposes into expanding concentric spherical shells, known as partial waves, each representing a different angular momentum state. This decomposition is the engine of scattering theory. When a particle approaches a target, we can isolate and analyze exactly how each specific angular momentum component interacts with the central force independently. Spherical coordinates provide the exact mathematical language translating the straight-line motion of a free particle into the complex rotational mechanics of a quantum interaction.